So I have already discussed the fundamentals of nuclear fission. Now I am explaining you again as per your request. So you know nuclear fission is one among the different modes of nuclear radioactivity. In fission, as shown in the screen in figure 2.1, a heavy nucleus splits into two smaller nuclei, and these two smaller nuclei are called fission fragments. And every fission event is accompanied by release of about 200 mega electron volt energy. In addition, a few neutrons, beta ray, gamma ray neutrons are also been released as products. And in most fission events, only two fission fragments are the byproduct. Hence, it is also called binary fission. And out of those, one heavier than the other. The probability of release of more than two fragments or release of equal fragment is called a symmetric fission, is very low. A heavy nuclei in this context refer to an actinide having atomic number 89, and all such nuclei are radioactive with specific probability for fission. And it is called spontaneous fission. The probability of fission is enhanced millions of times when a heavy nuclide is agitated by the collision of a particle. In a reactor, the fissions are caused by neutron absorption in a heavy nuclide like uranium and plutonium, and this is referred to as neutron-induced fission. Okay, so a neutron is bombarded in a nuclei, then a compound nucleus is formed, then the fission products like your neutrons and one larger nuclei and one smaller nuclei in binary fission, and two similar nuclei in symmetric fission are released. And this can be represented as neutron 10 plus uranium 23592 gives rise to compound nucleus uranium 23692, and then the products are formed in form of barium 13956 plus krypton 9436 plus 3 neutrons and 200 mega electron volt energy. Similarly, your neutron when bombarded in a plutonium 23994 gives rise to a compound nucleus plutonium 24094, and the products will be xenon 13454 plus zirconium 10340 and your 3 neutrons and 200 mega electron volt energy. The fission fragment nuclide are commonly in the mass range of about 60 to 170, spanning over 1000 species of nuclei. And the fission mechanism can be visualized through a liquid drum model of nucleus, about which I have told you in the previous class. And you can see there is a fission barrier as shown in the screen. So in the liquid drum model, you can well explain it. The original nuclei, then nuclear and Coulomb reaction, and the compound nucleus, then the Coulomb reaction, then the Coulomb force makes them separated, and two drops, and there is a critical energy and fission barrier, and you have the two fragmented nuclei. So if the target nucleus is a thorium 23290, then the last neutron binding energy will be 5.1, critical energy will be 6.5, and the compound nucleus will be having thorium 23390, and the threshold energy will be 1.4 mega electron volt. For uranium 233, your critical energy will be 4.6 mega electron volt, and your last neutron binding energy will be 6.6 mega electron volt, and the threshold energy will be 0. For uranium 23892, when the compound nucleus will be 23992, the critical energy will be 5.5 mega electron volt. The last neutron binding energy will be 4.9 mega electron volt, and your threshold energy will be 0.6 mega electron volt. Similarly, for uranium 23592, when the compound nucleus formed is having uranium 23692, your critical energy will be 5.3 mega electron volt. Your last neutron binding energy will be 6.4 mega electron volt, and threshold energy will be 0. And for plutonium 94, plutonium 23994, if the compound nucleus formed will be plutonium 24094, then the critical energy will be 4, the last neutron binding energy will be 6.4, and threshold energy will be 0. In addition of a neutron, would change the number of neutrons from odd to even or even to odd. This would specifically affect the pairing energy in the binding energy formula given under the liquid drum model. With Z fixed, when the neutron number is even, the pairing term is positive, and which gives more binding energy to the nucleus than when the neutron number is odd. This energy is available as excitation energy in the compound nucleus when formed. The compound nucleus de-excites by releasing this energy. One of its de-excitation mode is fission. So your uranium 235, when it captures a neutron, becomes uranium 236, which being an even nucleus has higher energy to be released. When uranium 238 captures a neutron, it becomes uranium 239, which being an even odd nucleus has less energy to be released. In other words, an excited even compound nucleus would disintegrate more readily than an excited even odd or odd even compound nucleus. So when we refer to the fission of a given target nucleus, we imply the fission of the corresponding compound nucleus. This is the reason why uranium 235 fissions readily irrespective of the incident neutron kinetic energy, unlike uranium 238 that shows a threshold. All nuclides in the actinide mass range undergo neutron-induced fission with different probabilities as thresholds. However, only few of them individually or in combination are suitable to be used in a reactor as fuel. Consequent to the interaction with neutrons and radioactivity, isotopes of actinides grow in number and variety. Several of these isotopes, though not intended as fuel, could also undergo fission in a reactor. So we'll limit our discussion to commonly used nuclear fusion fuels. The reactor cannot work without sufficient quantity of fissile material and as fuel. The only naturally occurring fissile nuclide is uranium 23592, and this is with abundance of only 0.7%, with the rest 99.3% of the element being uranium 23892. So this is an important point to note. However, through neutron interaction and transmutation, it is possible to produce other man-made fissile nuclides like uranium 233 and plutonium 239. And these two are man-made fissile nuclides produced in reaction or disintegration paths. Uranium 238 plus neutron is equal to uranium 239. This leads to neptunium 239, and this will leads to plutonium 239. Similarly, your thorium 232 plus neutron will yield thorium 233 as a compound nucleus, and it will then become palladium 233 91, and the resulting nuclei will be uranium 233 92. Then you know that most cases fission are binary, that is two fission fragments are released. They carry about 80% of the fission energy and hence are energetic. They are highly excited and unstable, and so disintegrate through alpha, beta, gamma neutron emission modes and or neutron emission modes. Fission fragment and those resulting due to their radioactivity are collectively called fission products. So while the fragments are positively charged excited nuclei, some of the fission products could have acquired electrons to become neutral atoms. Fission products could also include those fragments that have transmuted to stability. For a given energy of neutron, the excited compound nucleus like uranium 236 could split in many ways. The products are generally in mass range 65 to 170, each product having almost a definite probability of being produced. This probability is given by the fission product yield, which varies as the so-called M curve as shown in the screen. It may be observed that as the neutron energy increases, a tendency to favor symmetric fission increases, indicating that at much higher energies, say about 100 mega electron volt, the through portion in the M curve would disappear with symmetric fission mostly favored. The curve and its features grossly are similar across different fissioning nuclides, but with the maxima shifting slightly to the right as the fissioning mass increases. So yields per fission sum to 2 since each fission gives two products. And you can see two lines, the dotted line, En is equal to 0.0253 mega electron volt, and the solid line, En is equal to 14.7 mega electron volt. In y-axis, you have fission product yield per fission, and in x-axis, your mass number. So you can see asymmetric fission in the screen. So maxima in the fission product yield of 235 occur in the mass region of 95 to 100 and 142, 145 you can see in the screen, figure 2.3. The maximum yield is about 6 to 7%, that is over 500 times that of symmetric fission yield. So this suggests that asymmetric fission is mostly favored in the energy range relevant to reactors 0 to 20 mega electron volt. The explanation of asymmetric fission is given by the cell model of nucleus. Fission being a disintegration process, the product masses would tend to acquire higher stability. The cell model shows that closed nuclear energy cells correspond to high stability, leading to magic numbers of the nucleons. In other words, the fission product tends to acquire a magic number configuration of neutrons or protons or both. This tendency leads with high probabilities to a heavy component with proton number around 50 and neutron number around 80, and a light component with a neutron number around 50. So the reason for the tendency to maximize asymmetric fission by compound nucleus is to seek stable configuration for the products. Okay, so asymmetric fission is shown in the screen. The most fission products corresponding to maxima attain configurations close to magic numbers, they continue to be radioactive through other modes of disintegration to achieve stability. Most of fission products are beta minus emitters since their N by Z ratio is more than that required for stability in the corresponding mass number range. It is easy to visualize why fission fragments tend to have high N by Z. So, except for light nuclide, the proportion of N increases as Z increases. Thus, for some reasonable stability, N by Z for the actinide range is greater than the N by Z of the fission product range. However, when an actinide splits into two, the large number of neutrons that were present in the actinide is saved by the fission fragments, leaving their N by Z much greater than adequate for stability. So, the fission fragments are neutron-rich nuclides. So you can see energy variation of fission cross sections for uranium 233, 235 and plutonium 239 in the figure. And your fission cross section versus neutron energy for common fissile and fertile nuclides uh, has no threshold requirement for fissile nuclides, and the cross sections are order of magnitude higher at sub electron volt range than at a mega electron volt range, with many resonances in the intermediate range. For fertile nuclide, the threshold is close to 1 mega electron volt, as you can see. The resonances and the low energy cross sections for uranium 238 show sub-threshold behavior and are relatively very low and are often considered insignificant. So you can see how much energy is released in a fission in a tabular form as shown in the screen. The energies of neutrons produced in a fission, though small compared to those of the fragment, are very important since these neutrons can cause further fissions and other reactions which probably depend on their energies. Fusion neutron energy shows a continuous distribution called fission neutron spectrum and denoted by Xi, where E is the incident neutron energy and E dash the fission neutron energy. Since it has a feeble dependence on E, it is practically taken as Xi dash dot Xi dash D E dash. And you can see fission neutron spectrum in the screen. The fission spectrum for neutrons emitted in fission along with materials, you can see, and these are known as prompt neutrons. Most neutrons emitted consequent to a fission are prompt and are emitted within about 10 to the minus 17 second of fission. The number of neutrons emitted for fission denoted by nu, which is a function of E, is either 2 or 3 at a low, that is 0 to 100 kilo electron volt incident neutron energies, and could increase to about 4 to 6 in the high, that is mega electron volt energies. And you can see average number of neutrons emitted for fission in a tabular form in the screen. And you can be you may be very curious to know how the delayed neutrons could be important for reactor safety, while they are very small fractions of fission neutrons released. So you have to deal with reactor kinetics to understand it. The fission energy in a reactor is almost entirely caused by the neutron-induced fission reaction. Since every fission also releases a few neutrons, a chain of fissions would be set up if enough fuel is available. When a neutron causes fission, the fission neutrons released could cause further fissions, resulting in the next generation of neutrons. On an average, the time between two such generation of neutrons is a fraction of millisecond, that is 10 to the power minus 4 second in a thermal reactor which uses uranium-235 as fuel. This means that there are about 10 to the power 4 neutron generations in a second. Uncontrolled growth rate of neutrons would lead to uncontrolled growth in fission rate and in turn in the power. This is certainly a safety issue. So let us consider delayed neutrons of uranium-235 and the different delayed neutrons have different delay times with an average of about 10-13 seconds. The average generation time is found to be 0.006 into 13 plus 0.994 into 10 to the power minus 4, which is equal to 0.078 seconds. In other words, the effective time between two generations of neutron has increased from 10 to the power minus 4 second to 0.078 second. So the number of generations per second will be reduced to 12.8 from 10 to the power 4. So there is apparently a retardation in the neutron production, and the reduced to average neutron production rate helps reactor control and the safety. So there are some self-assessment questions you may try, and if you have any doubt, you can ask. Please try the self-assessment questions by yourself, and if you have any doubt, please ask. So I think you have no questions. Please go through the solution of those questions. So how to design a nuclear reactor we shall discuss in the next class, and this is very important. I have also discussed it earlier. So if you have any doubt, you can ask. Thank you.